Hello children, welcome back to the channel. Today we will be continuing our discussion of laws of motion, and the first topic that we will be dealing today is the conservation of linear momentum. Now the laws of motion, or the Newton's laws of motion, particularly second law of motion, gives us F equals to dp by dt, that is force is equal to rate of change of momentum. Right, we have discussed this in our earlier videos. If you haven't seen those videos, then the link to them is given in the description below. You may please refer to them. Now, if we say F equals to dp by dt, what we mean is that the applied unbalanced external force is equal to rate of change of momentum. If we have an isolated system, what it means is that as in the system there is no interaction with the outside world or the universe, which means that there is no external force, or in other words, for an isolated system, force is equal to zero. There is no external force, unbalanced external force, so no net force acting on the system. In that case, we must have dp by dt equals to 0. But by the definition, or by our understanding of differential calculus, we know that this can be true if P equals to constant, which means in an isolated system, or in a system where there is no net external force, the momentum is not going to change, or the net momentum is going to be conserved. This is known as the law of conservation of linear momentum, that linear momentum or net linear momentum of an isolated system remains conserved. It doesn't change at all. So if we have a system of n number of particles having momenta, say P1 for the first particle, P2 for the second particle, P3 for the third particle, all vectors, and so on, and Pn for the nth particle. In that case, the net momentum P is simply the sum of these momenta. So, in case of a system of particles, say n number of particles are there, they are moving about with different velocities, and the particles have different masses, so each particle have their individual momentum. However, as long as there is no external force acting on it, this sum, the net momentum, will always remain conserved, or it will not change. So in the system, at some point of time, if I take the net momentum, that is, say the sum of the momentum, and I take the momentum at a later point of time, say after some time, say 10 seconds, 15 seconds, 1 day, if the system is not interacting with the universe or outside world, then individual momentum might change. Remember that. Because let us say out of all these particles, n number of particles, two particles collided. P1 collided with another particle, say P3. After collision, their momentum might change. However, the net momentum, even after the collisions, if the system doesn't interact with outside world, or if there is no net external force on the system, then the net momentum after 10 seconds, 20 seconds, 1 day, 10 days will remain the same. The sum of the momenta, individual momenta, the sum of the momenta, not the individual momenta. The sum of the momenta is going to be the same. It will not change at all. Okay. Now, from this, a very interesting example comes. That example is about recoil of a gun. Let us say you have a gun. Which has a mass of m, capital M, say, and it is loaded with a bullet whose mass is small m. Okay. Now, if conservation of momentum is true, which is of course from second law we have already seen this. So the net momentum of the gun and the bullet system will remain the same when the gun is loaded with the bullet and even after the bullet has been fired. So if the bullet is fired from the gun, with some velocity v say, then the gun will also experience backward velocity given by say v. So what we have here is that two different conditions. First, the bullet was loaded and the gun was not fired. So what was the initial momentum? Because the system is stationary initially, so velocity of the bullet was 0 as well as the velocity of the gun was 0. This was before the bullet being fired. After the bullet was fired, the bullet has gained a velocity of v, the muzzle velocity, and as a result the gun also experienced certain amount of velocity. We want to find the value of this velocity, the velocity of recoil with which the gun will move backwards. That velocity can be found from the law of conservation of momentum. How? Before the bullet was fired, the net momentum was m into 0 plus capital M into 0. After the bullet has been fired, the velocity of the bullet becomes v. So the momentum of the bullet is m into v, and that of the gun becomes m into capital V. Conservation of momentum, initial total momentum is equal to final total momentum of an isolated system, because the bullet, while you fire the bullet from the gun, there is no external force, only the internal forces of the bullet and the gun is used here. So we have m small v minus of m small v equal to m into capital V. Therefore, velocity with which the gun will recoil will simply be minus m by m into small v. Now we know that the velocity with which the bullet moves out is very fast, say 1000 meter per second or 1200 meter per second or even faster certain cases. However, the gun will not recoil with the same velocity. Why? Because the mass of the bullet is much smaller compared with the mass of the gun. So this fraction m by m becomes very critical. As long as it is very small, this small fraction multiplying with the large velocity of the bullet will give us a very small value, and that's why the recoil velocity of the gun is not very large. If both the bullet and the mass were of the same, bullet and the gun were of the same or comparable mass, then the speed of the bullet and the recoil velocity of the gun will be similar. So the person firing the bullet will also experience the gun coming into him with almost the same velocity as the bullet. Now we move on to another important topic of equilibrium of concurrent forces. Now what is meant by that? See, concurrent forces means that forces acting on a single point. So under what condition, if there are different forces acting on a particular point, the point will be in equilibrium. What it means is that the acceleration produced will be equal to 0. We know that, say there are different forces F1, F2, F3 and so on till F and n number of forces acting at a single point, this. And if it is so, then these individual forces would tend to accelerate the body. So acceleration will not be 0. However, if these forces are such that the vector sum of these forces, which is given by say F, is equal to 0, then Newton's second law, F equal to ma, will give us that 0 vector equal to m into a. Mass of the particle or the object is not 0, therefore a must be equal to 0. So if the number of forces acting at a single point adds up to 0 or 0 vector, the sum of the forces is 0 or their magnitude is 0, in that case the point will not accelerate. Point of application of the forces will not accelerate, or it will remain in equilibrium. So if it were stationary, it will remain stationary. There will not be any acceleration produced. Now, this is the general case. Let us consider a special case of it where, let's say there are three different forces. Say F1 acting in this direction, then let's say we have another force acting in this direction, this say is F2, and then one more force acting in a different direction, say F3. The angle between F2 and F3 is say alpha. Angle between F1 and F3 say is beta, and angle between F2 and F1 or F1 and F2 is say gamma. Okay. Now this force diagram can equivalently be drawn by free shifting the vectors, because force is a vector, so we will be using the vectors idea. Let's say this has become, this is say F1, and then from head of this we take F2. Let's say this is F2, and then here this is F3. They form a closed triangle. We have learned in vector algebra that if different vectors, concurrent vectors, if a number of vectors acting at a particular point, or if a number of vectors, when we place them head to tail and they form a closed polygon, by polygon law of vector addition, the sum of the vectors will be 0. So these three vectors will have a net effect, or the resultant of these three vectors is 0, which means from this, these three forces will be in equilibrium. Now if it is so, then let us say, let's draw this like this, which will mean that the angle between F1 and F3, the angle between F1 and F2, this was gamma, so this will be gamma. The angle between F2 and F3 was alpha, so this will be alpha. And the angle between F1 and F3, the direction of F1 and F3 was beta, so this will be beta. So from geometry of the problem we can also see that this angle should be pi minus beta, this angle should be pi minus gamma, and this angle should be pi minus alpha, or 180 degree minus alpha, 180 degree minus beta, 180 degree minus gamma. In that case, this triangle, say A, B, C. If we apply law of sines, then what we get? This length AB, that is F1, divided by sine of the angle opposite to this. This is sine pi minus alpha, must be equal to this length BC, that is F2, by sine pi minus beta, must be equal to F3 divided by sine pi minus gamma. But sine of pi minus alpha is sine alpha, sine pi minus beta is sine beta, and so on. So we can write that F1 by sine alpha equals to F2 by sine beta equals to F3 by sine gamma. So for three concurrent forces to be in equilibrium, the ratio of each force to the angle between the other two, F divided by the sine of angle between the other two, that is the angle between F2 and F3, that is alpha, F1 by sine alpha, or F2 by sine of angle between F1 and F3, that is beta, so sine beta, and F3 by angle between F1 and F2, that is gamma. So ratio of the force and the sine of the angle between the other two forces is equal or is a constant. Okay. So each force, the ratio of each force to the sine of the angle between the other two is equal, are equal. This formula or theorem or is known as Lami's theorem. Okay, so here you are given that there is a string AOB, and at point O a force of 10 Newton is applied. Now this system, this part of the string OB and OA, and this force acting on point O is keeping the system in equilibrium. That is, the point O is not moving downwards or it's not moving upwards. The angle subtended here, AOB, is 90 degree. And this angle A is 30 degree and this angle B is 60 degree. You are supposed to find the tension and O in the string OA, that is T1, and the tension in the string OB, that is T2. To solve this, we can directly apply Lami's theorem if we know this and this angle, that is angle between F and T1, F and T2. We already know the angle between T1 and T2, that is 90 degree. Now the geometry of the problem gives you very easily that this angle is 120 degree and this is 150 degree. I am leaving it to you to find whether this is correct or not. Just apply simple geometry, you will be able to find that these two are the angles. Then Lami's theorem says that F by sine 90 degree, the angle between T1 and T2, must be equal to T1 by angle between the other two forces, that is T2 and F, that is sine 150 degree, must be equal to T2 by the angle between T1 and F, that is sine 120 degree, which implies that F by sine 90 degree is 1, so F by 1, that is F, must be equal to T1 by sine 150 degree is equal to sine 30 degree is equal to T2 by, this is equal to sine 60 degree. 180 minus 120 and 180 minus 150, these two. Therefore, T1 is equal to F sine 30 degree and T2 equals to F sine 60 degree, which is equal to, F is given to be equal to 10 Newton, sine 30 is half, which is equal to 5 Newton, and here it is 10 into root 3 by 2, which is equal to 5 root 3 Newton. Okay. Now the next topic that we are going to discuss is about connected bodies and free body diagrams. Now let's start with stating that up till now what we have discussed is that what happens if force is applied to a single body and how the body accelerates or how its motion changes. However, in real life situation you are always not going to get a single body being applied by a single or multiple forces. Sometimes it so happens that there are more than a single body, more than one body, and some forces are applied to it, and we are supposed to find the later stage or find the equations of motion for them. Let us take, for example, body of mass m1 and another body of mass say m2. Both are connected as shown in this diagram, resting on a frictionless plane, horizontal frictionless plane, and a force is applied on m1 from left to accelerate this. We are supposed to find the acceleration and also the force at the surface of contact where m1 and m2 meets. What is the force? Now, in such a system, what happens is that when F or the force is applied to M1, M1 transfers certain amount of force to M2. And as a result, M2 applies a reaction force on M1. So there will be an action and reaction pair acting at the interface between M1 and M2. In that case, it becomes a little difficult to draw the equation of motion or find the equation of motion from here. So what we do is that we take the masses separately like this. Let's say we call this M1 and we consider the forces acting on this, and then we also take the other mass M2 and we consider the forces acting on this. Now if we consider M1, what are the forces acting on it? First, the force that is applied F towards right, and then because of the contact, M will apply the reaction force on M1 in the opposite direction, that will be small f, say, which we are supposed to find. Second is that for M2, what are the different forces? Now for M2, there is only one force, that is the action force from F for M1 to M2. That will be in this direction and that will be F. Now this force alone will be responsible for the acceleration of M2, whereas M1's acceleration is the resultant of F and small f. Now since these bodies are connected together, their acceleration will be the same, that is the acceleration of M1 will be A, the acceleration of M2 will also be A. Now to find A, we take the parent equation or diagram and say that a net force of F is applied on a system of mass m1 plus m2. So Newton's second law will give F equal to m1 plus m2 into A, because both the masses will have to accelerate with the same acceleration. This will give us acceleration A equals to F by m1 plus m2. Now we can apply these to both the equations, however both the systems, say m1 and m2 separately. Now if I apply this to this equation, the equation of motion we will be able to find, but it will be having two forces. However, in this equation there is only one force, so it will be easier for us to find the force from here. For m2, what will be the equation of motion? Applied force F will give us the acceleration of m2, so it will be m2 into A. Therefore, F will be equal to, substituting the value of A from this that we have found here, it will be m2 divided by m1 plus m2 multiplied by F, and this will be our required solution F. So in case of connected bodies, what we have seen is that it becomes easier for us if we separate the bodies and take their respective forces acting on them and try to find the equation of motion. These diagrams where we take the connected bodies apart and discuss about their forces individually are known as free body diagrams. So this is the free body diagram of M1 and this is the free body diagram of M2. This becomes very handy when we talk about connected motion, we talk about motion over a pulley and that kind of problems. So understanding this is very, very important. We just need to separate the different masses that are connected in a simple or a complicated way, and then consider the forces acting on it and thereby finding the equations of motion for them. Okay, let's consider another example of free body diagram. In this case, you are given a uniform rod of length L and mass M. A force F is applied at one end of the rod. We have to find the tension at the interface of the rod at a point which is at a distance of L from the point of application of the force at this point. To do this, we can reconsider this particular diagram as the rod. We can divide it into two parts. This and so this has a length of L and this has a length of capital L minus L. And let's say it is connected by a massless inextensible string. So when we apply the force here, there will be a tension that will be generated here in this direction and here in this direction, T and T. We have to find the magnitude of this. So now we can use the concept of free body diagram here. We can divide this into two parts. One this and the other one is this. So on the left hand part of length L minus L, let's say it has a mass of m dash. The force that is being applied is tension. And on this there are two forces, F and tension, which will give us the acceleration of this part. Okay. So from this part, if I consider the left hand side, because there are two forces on the right hand part and the left hand part there is only one force, so it becomes easier for us. The equation of motion of the left hand part will be, since m dash is the mass, m dash into say acceleration. What is A? A is the acceleration produced by this force on the rod. So our problem will be solved if we can find m dash and A. Now what is m dash? M dash is the mass of the rod whose length is L minus L, capital L minus L. How to find this? To do this first, we will first consider or remember that we were given a uniform rod of length L and mass m. So m divided by L will give us mass per unit length of the rod. So if m by L is mass per unit length, what will be the mass of length, this length, L minus L? We just have to simply multiply it by L minus L. And this will be our m dash. Second is, what is the acceleration? Newton's second law to the whole rod will give us F equals to m into A. Or we have A acceleration equals to F divided by m. So we have found m dash. Yes, we have found A here. Therefore, tension T will be m dash, that will be m divided by L into L minus small l, and A, that will be F by m. Or simplifying, we get T equals to 1 minus L divided by capital L into F. So this tension is dependent on the small l. Larger the value of small l, the tension will keep on decreasing, and smaller the value of L, small l, the tension will increase, which means that if this point is taken towards right, the tension will be higher. If it is towards left, the tension will be lower, which is necessary because if we move this direction, this length increases, means the mass of the length on the left increases, which means we will need more force to accelerate it. On the other hand, if we move this line towards left, mass of the remaining part, that is L minus L, will be shorter and so smaller, and so mass will be smaller, and so we need lesser tension. Time for a bonus problem. Let's say we have a balloon here having a mass m. When it's released in the air, it accelerates downwards. Its acceleration is given by A, downwards. Now, if we take out some air or gas out of the balloon, that is to say, if I take some gas out that is of mass m, if we take mass m out of the balloon, which initially had mass capital M, then what we see is that the balloon starts accelerating upwards. We have to find the mass m. This mass m, what is the value of the mass m? So how much mass needs to be taken out of the balloon so that instead of accelerating downwards with an acceleration a, it starts accelerating upwards with the same acceleration a. The solution to this problem will not be given in this, or we will not be solving this problem right now. What I would like to ask you is to try and solve this problem and put it in the comment. We will discuss this problem first thing in the next video, which will be uploaded at the same time tomorrow.